Here we are going to discuss how to use machine learning to identify art paintings by artists based on ideas in a paper done by Stanford undergraduate students in a computer science class. Okay, so here are the results. They classified in two different ways. In one case, they did a binary classification where they're just comparing one artist to another, and the classification rate is quite good. And in another case, they put 7 artists in the same classifier, in a single classifier, and here the overall accuracy rate is 85%, and it varies a little bit from artist to artist. Now the trick here is you need to extract data from these images, and what kind of data do you want to extract? Well, this paper used something called histogram of oriented gradients, and we're going to discuss what those are. Okay, so you start with a painting, and this is a Picasso, and then you convert it to grayscale, and now we're going to zoom in up on this little section up here to describe the processing that we do on each one of these images. Okay, so now here's the image at the pixel level, a very tiny section of it, and of course pixels are just numbers that get converted to a color by the computer, and for grayscale, 0 is black, white is 255, and all the gray values are somewhere in between. And so to process this, we put a grid on it, a numeric grid, a 3x3 numeric grid, and we multiply the pixel values under each one of these numbers. So we've got -1 for this column, 0 for this little column, and 1 for this column. Now we multiply, so we're going to wind up with 9 values, and we add all of those together and then divide by 9 and store the result at this pixel. And then we move over 1 column, and so we're going to get the values for the pixel right next to this pixel. So we got the value for this pixel here. Now we're going to get values for the second pixel. And we're going to do this across the whole complete image. And we're going to, of course, drop down. So we're going to process the whole image using this method. And it will actually give us a new image. And here's the new image. And what this image is, it actually represents the partial derivative in the x direction. And it's capturing the slope. So where the intensity in the image remains the same, so here the intensity is the same. Over here where it's all white, the intensity is all the same. And so where the intensity is the same, the numeric values that represents that intensity are all the same, so their slope doesn't change. And so your derivative, capturing the slope, this is going to be a 0 slope. But where you get an edge, like you get here, that's going to change intensity value. It's either going to get darker or it's going to get lighter. And so first it gets darker, then it gets lighter, and so these are the slopes. So this means the slope is actually decreasing where it's dark, increasing where it's light. And if you notice, the vertical edges stand out. The horizontal edges don't stand out very much, and that's because we've only gone in the x direction. We also need to do the same thing in the y direction, where we're going to get the partial derivative in the y direction. And to do this, we take that same grid and it gets transposed, and it moves in the other direction. And so now if you notice, we're getting the horizontal lines are emphasized, the vertical lines not so much. Compare it again. Okay, so here's the horizontal line, it stands out. But it's the same idea, we're capturing the slope, not quite the instantaneous slope like what you do normally in calculus, but a good approximation of it. And so now we're actually, those gray images are capturing the direction of the slope. We're actually not interested in the direction. We just want the magnitude of the slope. So for each of the pixels in the x image, in the x, that's the x derivative, that's the derivative in the x direction, we're going to square the values one at a time, and then we're going to do the same thing for the y's, for the corresponding pixels, and then we're going to add those together. And it's basically the Pythagorean theorem to get the combination of the x and y slopes or derivatives. And now we also, each one of those edges has an angle, and so we want to know what that angle is. And to do that, we just use trigonometry, and we get the angle whose tangent is represented by these values. and there's going to be one angle for every single pixel in the image. Now, if we process the image using the gradient formula, we get the same, in many ways, the same as the gray, except the difference is just how the slopes are represented. So here, a zero slope becomes zero. It's not gray any longer. And the edges, because they're just magnitudes, we no longer know the direction of the slope. We just know there's an edge there. And so these become white, or the edges become a light color. We never get a dark color for an edge. And the black is just where the slope is basically zero, where it's not changing, where intensity isn't changing. So then we actually section the thing off into grids. And now each grid, now we have the information. We know at each point we know the angle of the gradient. We also know the values of the gradient. So what we do is we build a histogram for each one of those sections, and we put things in buckets based on angle range. So we take all the gradients, for example, all the gradients, we sum them all up where the ranges are between 0, the angle of 0, and the angle of 20, and we get this bar. And then here we get between 80 and 100, and we get this bar, and that's the sum of all the gradients that have that angle. And we do it for every section, so we get a histogram for every one of the little sections. And then we concatenate all of these histograms, which gives us a vector, because each bar in the histogram is just a scalar value, that's all it is. And this becomes a vector that we can put into a regression. And each one of these bars can be thought of as an independent variable, and then the dependent variable is a classification number we assign to each picture. So say Picasso, we could give it a 1, and we could give all the Picasso paintings a 1. We'd give all the Van Gogh paintings a 2, and so forth. And then we put this into a regression classifier, and that's how the classification takes place. Okay, so now we're just going to look at the gradient versions of a Picasso and a Van Gogh and compare them. So there's the Picasso, there's the Van Gogh. We compare them. So intuitively it makes sense, because if you look at this, I mean, obviously there's the angles, there's many, many more angles in the Picasso painting, I mean the Van Gogh painting, and there's also a lot more edges in the Van Gogh painting. And over here we've got the angles are quite limited compared. These are like sort of circular, and these are very angular and sharp like squares. And so it makes sense that this would be a way to separate these two artists using a regression style classifier. And the command for building that thing called the hog is quite simple. This is a command that comes with the R programming language that will do it. You just put in your painting, and it gives you ultimately that vector. But of course, you'd want to teach this in a sort of systematic way to get students to understand that calculus is being used, trigonometry is being used, the Pythagorean theorem is being used, and then histograms are even being used. So there's a lot of mathematics going on here. And so I think it's an interesting application of math that may not have been seen very much in a high school setting.